first one to prove it, and he used the simple continued fraction expansion to do it. But we will do it now in another way, following a proof which was first introduced by Fourier. And the series 1 over n factorial will be our starting point as the definition of E, where n starts at 0 and goes to infinity. And now let us see what happens if there would be an integer p and a natural q such that E equals p over q. Okay, since we've had all natural numbers in our series and just a few, we must at some point find our q. Let's subtract everything up to this point, and if you do now multiply by the factorial of q, then right at the start you might already see q factorial over q must always be an integer, since you can cancel out q, and cancelling out is what we are gonna do with the rest of these fractions, because we can see the whole denominator will now always be contained inside the numerator. So we can say this cancels out and leaves an integer. Okay, and we can now conclude for the left hand side it must always be an integer. Alright. Euler's number is irrational. Euler proved it, so there is no debate. Euler's number is irrational, and it's about 2.718. And if we now take a look at the right hand side, we will again see factorials, which we have to divide, only this time the numerator factorial of q is contained in the denominator, which leaves you with 1 over a product. And there you can see this product just gets longer and longer. And if we observe every single factor is bigger than q, so every single factor must be at least 2, then we know that every time we only write 2, the denominators will have to get smaller. So you know the whole fraction has to be bigger right now. But for this series, I'm just gonna show you how you can visually see what this has to be. Just take a half and a quarter and an eighth and see how it gets closer and closer to 1. So you know this series converges to 1. But then we show that our right hand side must be smaller, which is tough because we stay greater than 0 if we add positive stuff. But there clearly is no integer between 0 and 1. So this is the point at which we have won, because this contradiction right here shows you why no matter which p and which q you would try, it can never work, and therefore we see E can be rational. QED. Euler's number is irrational. Euler proved it, so there is no debate. Euler's number is irrational, and it's about 2.718. 2818 28459045235360287471.
So rain
formula, you will see that you get the solution in the very next step. Just sing the song in your head. Negative b plus or minus the square root of b squared minus 4ac over 2a. Negative b plus or minus the square root of b squared minus 4ac over 2a. Okay, let's start with our equation, and our job is gonna be solving this now for x. So let's take minus c, multiply by 4a, and if you now add b squared, it all looks way too complicated. But don't be scared, just take a close look to the left side and you see there's a binomial formula with 2ax and b. So altogether this is the square of 2ax plus b, and now we have only 1x. So the next step will be to get rid of the square. And if the right side is not negative, the square root must be one solution. But there's an alternative, because minus the square root yields the same if you square it. So we write plus minus, and now we are at the point where it only takes 2 more steps to solve it for x. And if you look to the left side, you know what will be next. Subtraction of b and division by 2a is giving us a formula for x. Okay, and it's negative b plus or minus the square root of b squared minus 4ac over 2a. Negative b plus or minus the square root of b squared minus 4ac over 2a. Negative b plus or minus the square root of b squared minus 4ac over 2a. Negative b plus or minus the square root of b squared minus 4ac over 2a.
14159, this is pi followed by 2653589, circumference over diameter 79, then 323. OMG, can't you see? 8462643, and now we're on a spree. 38 and 32, now we're blue. Oh, who knew? 7,950, and then a 2. 88 and 41, so much fun. Now we're on 97169399351. Halfway done. 58 now, don't be late. 209, where's the wine? 74, it's on the 4, the 94459. 230, we gotta go. 78, we can't wait. 164068, we're almost near the end, keep going. 62, we're getting through. 089 out of time. 862, 8034, there's only a few more. 82, then 53. 42, 11, 7, oh, and 67. We're done. Was that fun? Learning random digits so that you can brag to your friends.
Are you ready for more? Well, here's another 100 digits. 9, 8,
There's a very large
1,
out
4, 80865. All high 5. 13, 282. Look at you. 306. 6470. If you go slow. 938 4. Then you will score 46095. Now let's dive 505 into more pie. 8 blue flying bats over 2 gold cats.
23 shoes, 172 screws.
5 well-dressed small dogs working 35-hour jobs.
Oh, this song is so absurd, just rhyming pure random words.
94081, can you taste your tongue?
28481, it just can't be done.
117450, now close that door. Get those numbers in your brain and keep them forevermore. 28410270, let's make a stew. 1938521105559. Now all final run. 644622948, look at you. 95493038119, and wow.
Now let's learn 100 more.
6442880 all went on a big blind date and ordered in plates full of food. 97566 all wearing their brand new kicks in 5 different shades of a blue. 933 all climb up a tree to see for miles and 46 clouds. One thing you won't forget is 2847 next and more than 5 friends is a crowd. 648 the science is to wait till 233 are in queue. 7867 and hey, there's no line cutting for you. Now the most important rhyme, just take a look right at the time. 83166 5. Next, look at you, flex 2712. If this is boring, that's on you. Oh, and I know not won the race. You have almost won with 456 fans. 4, 8, 5, 6, 6, 9. They're all waiting in a line to clap 34 of their hands. 6, 0, 3, 4, 8, 6. Now go pick up 10, big 64. We start 5 little fires. 4, 3, 2, 6, 6, 4. Let's blitz for the final show. 8, 2, 1, 3, 2, 9, 2, 6, 0, 726. 2, 4, 9, 1, 4, 1, 2, 7. But now you know. Pi 3.0.
The integral of cosine from 0 to the half of pi is exactly 1. And here is why. The integral of cosine from 0 to the half of pi is exactly 1. And here is why. If you take a point on the unit circle rotating around with the constant speed of 1, and you look now at the projection of this into the vertical line, the orange velocity will always align with the height of the blue one. But just from the top of my head, I don't know what this is, but if we stop right here and call this angle x and look at this right triangle, you might see next we have the same triangle right there, so at the top must be x. And being aware that the hypotenuse is 1, we can see next the orange velocity is the cosine of x. But integrating a velocity will always be just the distance traveled. And now you can see if x goes from 0 to the half of pi, the orange point traveled a distance of 1. That's why the integral of cosine from 0 to the half of pi is exactly 1. Here is why. The integral of cosine from 0 to the half of pi is exactly 1. And here is why.
If you wanna derivate with me, I know a strategy that you can master in no time. First we'll be beginning with a method that is winning called a power rule. You'll do fine. Coefficient to the side, then we'll multiply. Start to bend on the high. If you're feeling like you need a little bit more help with me, you met me at the perfect time. You want me, I want you, baby. The power rule, I'm derivating. And -1, we're calculating. Power rule, multiply the base by powers higher than you. Subject to exponents by 1. I'm derivating. Rule, multiply the base by powers higher than you. Subject to exponents by 1. I'm derivating. The chain rule the greatest, ain't no debating on it. I'm still derivating, I'm heavily dedicated. It's kinda like power rule, but there's a small addition. It tells you that x is an isolated parenthesis of x called g of x the function. Needing problems to solve, so let's take it back to the basics. You see what you got me out here doing? Multiply it by parentheses, exponent. Let's go. fx, power rule, same method. And -1, prime gx to multiply it. I had to get the a for all the values I've been making. If I had to slip, I fall to solve another derivation.